let's try to solve this problem here. A 75 cm long wire of mass 2.25 gram is under a tension of 400 Newton. So let's try to sketch this situation over here. So you have a wire and the length of the wire is 75 cm. Let's convert it into meter just to make things convenient for us. So 0.750 meter. And it has a mass of 2.25 gram. Again, let's change it into kg. So this will be 0.0. I'm worried that I might make mistakes with exponents. So let's just make mistakes for shifting the decimal place. So let's just write 2.25 times 10 to the power of negative 3 kg. Okay, it's under a tension of 400 Newton. So this string here is being stretched tight. So there's tension being exerted on this string, and the tension is 400 Newton. Okay, the wire is vibrating in its third harmonic. Okay, so now in question A, they ask you to sketch the waveform of the vibrating wire. Okay, so let's try to figure out how does a third harmonic looks like. Okay, so for harmonic, right, harmonic is basically the n number. So for this one, n will be equals to 3. Okay, so let's start by roughly going through how does a fundamental looks like first. Then from there, we progress to the third harmonic. Okay, usually what I will do is I will sketch an equilibrium line first. If it's a stretched string situation, I will sketch an equilibrium line here. Okay, so we know that it's a stretched string, so the two ends are being whole, only that you're able to stretch it, right? So because you hold the two ends already, the two ends basically cannot move up or down. You are stretching it tight, you cannot move them up or down. So the two ends here, because they cannot move, they will form nodes. Okay, so we will know that at both ends there will be nodes. Okay, nodes at both ends. I can probably pin it down. Okay, so we know that nodes and nodes cannot sit together. Okay, nodes and nodes must be sandwiched by an antinode in between. Okay, so you know that there will be an antinode in the middle. Okay, that's the simplest way to construct a standing wave. Okay, you cannot have just two nodes only. In between the two nodes, you need to put in an antinode. So this is the simplest standing wave that you can make, and this is what we call as the fundamental tone or the first harmonic. Okay, if you wish to step up to the next harmonic, which is the second harmonic, what you can do, the next simplest thing that you can do is to add one more note inside. Okay, so if you add one more note inside, then the situation will be having one note inside. Again, note and note cannot sit together side by side. You need to split them apart with an antinode in between. Okay, so this will be what we call as just now the first harmonic, now the second harmonic. Or if you want to call it by tone, this is the fundamental tone. This will be the first overtone. The first time going over the fundamental tone. That's the meaning of first overtone. Okay, but we are not stopping here. We want the third harmonic. So the next simplest thing that we can do is not to have one note only, but to have two notes on the string. So you can have one note over here, another note over here. So now to split all the notes so that they don't sit side by side, we put antinodes in between. Okay, so this will be the third harmonic, or so known as the second overtone. Okay, so we are clear with how should the note and antinode be arranged already. Right now, I'll remove the first overtone and fundamental tone. I'll remove all the other harmonics because those are not relevant. We only wish to know the third harmonic only. Okay, so I'm going to redraw a bit of stuff over here. Just now was just to let us know how to arrange the note and antinode. So for me to sketch, usually what will I do? Again, I will start by sketching an equilibrium line. Then I pin the two ends of the string. Then for antinode, it will be above the equilibrium line. For node, it will be on the equilibrium line. This will be below, above, below. Okay, so if I sketch my line, if I sketch my standing wave pattern, it will be something like this. Okay, so I know that standing wave, it oscillates repeatedly, changing its direction. So I know that there will be another direction as well for our standing wave. I should mark before I sketch. It looks nicer. Okay, so this will be the other way around. Okay, we know that it keep on change direction. Okay, so this will be the standing wave, but usually I won't stop here. What will I do? I will label what is the length of the string. The length of the string will be from here to here. L. Okay, if they give you the length already, you can put it in. It's 0.750 meter. Then I'll also label as well where is lambda over 2. We know that distance between successive nodes means by the next node, the distance between one node and the next node, the distance is always half a wavelength. So we know that there will be how many times half a wavelength? 1, 2, and 3 times of half a wavelength. Okay, always know that distance between node and the next node, it's equals to lambda over 2. So now we have 3 lambda over 2 that can be equated. There's 3 lambda over 2 that can be equated to the length of this string over here. Okay, so this is my complete drawing for the waveform. Okay, question A. Okay, next. For question B, determine the speed of the wave in the wire. Okay, for stretch string, right, you have to be very clear that the speed, right, there's 2 types of speed involved. One is the speed of the wave in the wire or in the string. Okay, another speed that can be involved is the speed of the sound produced by the wire. Okay, this one is the speed of the progressive wave moving in the wire, because you know that there's a string. If you plug it, there will be progressive wave traveling to the left, reflected to the right, they overlap, then they produce a standing wave, right? That this V here is representing the speed of the progressive wave in the wire. But this V sound over here is the speed of the wave, of the sound wave produced by the stretch string. Let's say the stretch string is a guitar string. So if you plug it, then the surrounding air will have a sound due to the vibration of the air particles. So this one, V sound over here, is the speed of the sound wave produced by the string. And because this one, the medium is air, this one, the medium is string, because they have different medium, their speed should be different. Okay, so every time when it involves speed, you have to be very careful what kind of speed are they asking for. Are they asking for the speed of the wave in the wire, or are they asking for the speed of the sound produced by the wire? Okay, so in this case, this is the speed of the wave in the wire, so this is V wire. So if this is V wire, we know that it can be related to the equation that you can learn, that you pick up from lecture, which is V is equals to square root of the period divided by the mass per unit length. Okay, this one, you cannot use V is equals to square root of T over mu. This one is not allowed for V sound. Okay, you have to be very clear about it. So in this case, it is allowed, no problem to use it. So V is equals to square root of the period divided by the mass per unit length. We know that the mass per unit length, if you expand it, it will be mass divided by the length of the wire. So now it's just, you are just left with substitution. 400 Newton for your tension. The mass is 2.25 times 10 to the power negative 3 kg. Make sure everything is in SI unit so that you can form your velocity with the correct unit. The length will be 0.750 meter. Okay, so if you put everything in, do your calculation, I believe you'll get 365.15. Okay, meter per second. And this is the speed of the progressive wave in the wire. It is not the speed of the sound produced by the string. Okay, you have to be very clear to differentiate these two things. Okay, next, obtain the frequency of the sound generated by the wire. Now you see, now they're asking for sound generated by the wire. So this is the frequency of the sound. Okay, let me write it down. Okay, V of the wire is different from V of the sound. But how about the frequency of the wire and the frequency of the sound? Well, okay, not going to hold you back. I'm just going to tell you that they should be equal. Why should they be equal? It's actually quite logical. If your string vibrate once, then the air particles should follow and vibrate once, right? Okay, your guitar string up, down, up, then your air particles will also go up, down, up once. Okay, so every time you vibrate once, the wire vibrate once, the air particle should vibrate once. So if the wire vibrate 100 times in a second, of course the air particles also vibrate 100 times per second. Okay, the frequency should be the same. Okay, so because we know that V is equals to F lambda, so we can make a conclusion that the lambda of the wire is very different, should not be the same as the lambda of the sound. Okay, because this one is same, this one is different, so what conclusion can you make? The lambda will be different. Okay, so you have to be very clear what are the same, what are different. So because for this situation, they are looking for frequency of the sound, and you know the frequency of the sound is the same as the frequency of the wire, so therefore you can solve it using V is equals to F lambda for the wire. Okay, that is fine to do it, because later that you get the frequency of the wire, it's still the same as the frequency of the sound. Okay, so that is what we are going to do. We are going to do V F lambda for the wire. Okay, so this one, the V we already obtained for wire is 365.15. Frequency is what we want to obtain. The lambda is what we need. Okay, we can look back in this thing over here. We can see that L is equals to 3 times of lambda 3 over 2. I'm labeling 3 because it's the third harmonic. Third harmonic, n is equals to 3. Okay, so I know that lambda 3 is equals to 2 over 3 L. Okay, so what am I trying to do here? I'll replace the lambda over 2 here, lambda over here with 2L over 3. Okay, replace. I know that it's 2 over 3L. All these things is for wire. Okay, so it's not for the sound. Okay, so 365.15 frequency, 2 over 3, the length is 0.750. So from here, I'm able to get the frequency of the wire to be 730.30 Hertz. Okay, this is for the wire. But we know that, okay, let me write it up here. Frequency of the wire is the same as the frequency of the sound. So therefore, I can say that frequency of the sound is equals to 730.30 Hertz. Okay, so this is the correct way of understanding it. But if you are not aware that these two are two different things, one is measuring the wire, one is measuring the sound, you will still get it correct because if you just use the value given up there, right? But actually there's a little bit of things that you need to make clear of, where the V can be different for sound and wire, but the frequency are the same. That's why you can calculate the frequency of the wire first and equate it to be the frequency of the sound. Okay, so that's it for this question. Thank you very much.